Okay, I'm going to go over how to solve a weak acid problem because I'm not going to be in class today, so I thought this might be useful to you. So in this one, it talks about hypochlorite ion, blah, blah, blah. The main point is we're going to try to figure out the pH for a weak acid. So this is an equilibrium between the molecular form and the ionized form. So here is the dissociation reaction. I'll show it in the simple form, like that. And we know that Ka for this, which is the equilibrium constant for the dissociation, the acid dissociation constant, has that value. That shows us that it's a very weak acid because it means that the acid is mostly molecules and only a small percentage of it breaks into ions. So now I'm going to basically set up my ice table. And here's what I'm given. It's 0.1 molar solution of acid when we start, so I'll put that in. We'll assume that there's no initial hydrogen or hypochlorite ion. Since that's true, the equilibrium proceeds to the right, so we lose X amount of hypochlorous acid, and we gain X in hydrogen ion and X in hypochlorite ion. So at equilibrium we have 0.1 minus X, X, and X, right? So now we just set up the equilibrium expression. Ka is hydrogen concentration, hypochlorite concentration over undissociated acid concentration. And now we basically have all the components of our expression. 3.5 times 10 to the minus 8 equals x times x over 0.1 minus x. Now I don't mind if you use a solver here, but just as before, the 5% rule works almost all the time. So if we go ahead and solve this for x, we can assume that 0.1 minus x is about 0.1. This is again the 5% rule. And so when we do that, our expression reduces to basically 3.5 times 10 to the minus 8th is x squared over 0.1. If we kind of just turn that around and solve it, we get x squared equals 3.5 times 10 to the minus 9, because I'm multiplying the 0.1 to both sides. Right. And then if I square root both sides here, I get x equals, getting into the calculator, square root of 3.5 times 10 to the minus 9. I get about 5.92, pardon me, times 10 to the minus 5th molar. Now, if that's x, that's also my hydrogen concentration. So I could use this to figure out all the concentrations. The concentration of the acid is still about 0.1 molar, right? Because subtracting this is making almost no difference. The hydrogen is now equal to x, and the hypochlorite, if we care to know, is also about 5.92 times 10 to the minus 5th. And since pH is equal to the negative log of the hydrogen ion concentration, we can now find that the weak acid concentration, or pH, is negative log of 5.92 times 10 to the minus 5th, which comes out to about 4.2 as the final answer. Okay? So that was finding the pH for a weak acid. Now, just for the sake of comparison, I think it's important that we notice how it would be different should we have done the similar calculation for a strong acid, right? So, like, just for the sake of argument, if we had done this for a strong acid, for example, hydrochloric acid, which goes 100% to the ionized form, if you had started with a 0.1 molar solution of this and none of these, you would have lost all 0.1 molar to dissociation. You would have gained 0.1 molar of each. And so at equilibrium, you'd have effectively none of this, 0.1 of this, and 0.1 of that. Which means for the strong acid case, where Ka is very large, the pH would have just been the negative log of 0.1, which is basically 1. So notice that even though they have the same concentration, the pH of a weak acid is considerably higher, meaning less acidic, than the pH of a strong acid at the same concentration. Okay, thank you.